Good morning, folks. I am not Will Habeck. I am Mark Foster. I'm also from NASA Ames. Will, unfortunately, was sick and isn't able to make it this morning. Hang on for a second. So although you're a small group, I'm glad to see you here. It's a concentrated group. We're pleased to welcome Professor Mirkovic from USC. Her research focuses on malware analysis, denial of service, and privacy. I'm really enthusiastic about what she's going to present to us. There's some of it's generic, but it will apply to our campuses. It will apply to organizations like NASA. And I think that what she's going to tell us about the challenges and potential solutions for a security service for the internet is very intriguing. And I encourage you to take this and take it back to your organizations and be inspired by some of what she's got to tell us.
Thank you. Thanks everyone for being here. I'll talk about our solution for denial of service and prefix hijacking called SENSS. It's a collaborative solution, and we've had about 2 years of development and testing and prototyping, and now we're ready to transition this to practice. So I'm talking today hoping to have some people interested in trying this in your own networks. This is joint work with Minlan Yu and Shivaram Ramanathan from USC and Ying Zhang from HP Labs. So I'll start by motivation. There is growing trend in DDoS and BGP prefix hijacking. We've seen increased frequency of attacks, and we've seen large increases in volume. Looking a few years back, we're seeing attacks of 1 to 10 gigabits per second, and in 2014, we've seen 400 gigabits per second. This year, we've seen something around 600 gigabits per second, and 6 months ago, at Nanog, people have reported even 750 gigabit per second attacks. So these are a huge volume of traffic that networks just cannot handle themselves. In BGP prefix hijacking, we've seen increase in the frequency of the attacks. These attacks are especially severe because all your traffic goes somewhere else, and this can happen. This can have duration anywhere from a few hours to up to 60 days. So we've started looking at this from the angle of being a distributed threat that needs a distributed solution. There are a lot of solutions today that are either localized or cloud-based. They work fine in some cases, and in some cases they just don't work at all because you cannot handle this type of attacks in one point in the internet. So we started looking at the following variants of denial of service. These are direct floods that just send a lot of traffic to the end network directly. The end network cannot handle that itself. Reflector attacks that where the attack goes to the reflectors and the answers go back to the victim network. The attack traffic is spoofed. The answers look perfectly legitimate. They're hard to filter at the end. Because usually, again, they are high volume and they overwhelm the link between the end network and the ISP. The crossfire attacks have been recently proposed. We haven't seen them in practice. We've just seen them in the research papers. In the crossfire attack, there are many sources and many destinations where the attack flows, and it converges on a bottleneck link that is shared between the client and the client to victim traffic. And this is very hard for the victim to diagnose and to handle because the bottleneck is somewhere upstream in an ISP that is carrying traffic to the victim. In BGP prefix hijacking realm, the attacker can announce that it owns the victim prefix and thus attract the traffic to itself, or it can announce that it is close to the victim's prefix, and some networks that are close to the attacker will adopt this fake route. So all the victim traffic in both cases goes to the attacker, and the attacker can drop it, or he can sniff it, or modify and reroute back to the victim. I'll go quickly over the operational approaches to attack mitigation. There are a lot of research approaches too that I'm not covering simply because they are often not deployed, and they are often not deployed because they require big changes to the internet, big changes to the routers, and this is not realistic. It won't transition to practice. So we wanted to find the middle ground where we can do something better than the operational solutions today, but it is also easily deployable in today's networks. So today, an network could buy a DDoS mitigation device to handle DDoS attacks that will do some very sophisticated analysis of traffic, maybe some deep packet inspection, and it sits at the end network. And it's very good at handling some types of attacks that are sophisticated, low-volume application-level attacks. However, if you're slammed with traffic that overwhelms your link to the ISP, then there's nothing at the end network that you can do to handle this. The other solution for end networks is to go to a cloud-based defense like Cloudflare that is geographically distributed. It's alike to CDN. But it also does some traffic scrubbing. And this traffic scrubbing is proprietary, so the cloud will attract all the victims' traffic to itself. It is big, it can handle it. It will do some, again, analysis, proprietary analysis, drop something that it thinks is attacked. And this works in some cases. If the network that is under attack has dynamic content, the client traffic needs to be rerouted to the end network after scrubbing. It's an expensive solution. It's not something that every network can afford. And ultimately, you're offloading the handling of your traffic to someone else. So it's something that works for some networks, may not work for others. In BGP prefix hijacking, really all solutions aim at withstanding the attack and preventing the attack. So there is BGP Anycast, where again you can distribute the advertisements for your prefix geographically, and this makes it hard for the attack to succeed because the fake routes are not better than the true routes, so there will be very few networks that adopt a fake route. Again, this is a solution that is expensive, and it's preventative in a sense that you have to have it in place at all times. You cannot just have it when you're under attack. Our solution called SENSS enables victim to observe and control its traffic and routes in remote ISPs. So the victim can ask to observe the traffic either going to its prefixes or carrying its prefixes as a source, or to observe routes to its own prefixes. It can ask to also filter or allow different traffic going to its prefixes, and to control its own route by demoting routes that it thinks contain the attack segment. And it can ask this of any willing ISP, even if that ISP is not a neighbor of the victim. So our solution is a collaborative solution. It can work between a customer and its ISP, its first hop ISP, or it can work between any end network and any ISP in the internet that is remote. What is needed for this solution? So this aligns the ownership of traffic and routes with the ability to have a control over the traffic. And we believe this is a good property of this solution. And the only thing needed to secure it fully is that the ISP needs to be able to verify that the requester has the authority to speak about a given prefix. It either owns the prefix or it has been given authority to speak about the prefix by its owner. And so I'll go over how we do that in a few slides. So the operation of SENSS works in the following way. The ISPs run a SENSS server. The SENSS client runs at the end network. And when the end network is under attack, it decides which SENSS server to talk to. In sparse deployment, this would be the SENSS server deployed in its immediate upstream ISP. If we had very large deployment, there is a way to do a SENSS directory service. You can advertise using DNS. You can build a separate service so that the victims could identify which servers they need to talk to. The victim sends usually a query to SENSS server. The SENSS server authenticates this query. ISPs could also decide to charge for this service. This could be an add-on value, and the victims would pay on demand. So when they are under attack, they could request a service. They could pay for every service that is rendered. The ISPs authenticate each request, charge if they have any charging scheme, process it, and then if it's a query, they return the results back to the victim. If it's a control request, they enact the control decisions. And this could happen in many rounds. So the victim could have some observations, make some decisions, what to filter, enact these decisions, observe again, figure out that the attack is not properly handled, and go to a second round until it's satisfied with how the attack is handled. All the intelligence here resides at the victim. So the ISP is simply providing a very, very basic service that they can easily provide with today's infrastructure. The victim is the one that decides what will happen. And there are different ways we can allocate the client functionality. So the client functionality can reside at the victim. If the victim is not technically savvy, if the ISP wants to take over the total detection and mitigation of the attacks, then the ISP can also run the client at its own side and leave the end network out of the picture. These are the SENSS APIs that the ISP would expose. They are intentionally simple because we wanted them to be deployable with today's infrastructure. So the victim can send a traffic query specifying a flow it needs to observe. This could be all traffic going to the victim's prefixes, or it could be traffic in a certain category. The flow definition is compatible with the open flow definition, so any combination of the IP and transport header fields goes, and you can also have the wildcards. The victim could ask for a direction too, so it could ask for incoming traffic into the ISP, or it could ask about outgoing traffic, or it could ask about traffic that the ISP itself generates. And there is the observation time for the request. The ISP then observes traffic for this amount of time, aggregates the responses, and sends them to the victim. Each response consists of a tag that identifies the incoming link or the outgoing link, the peering link between the ISP and its neighbors, the direction of the traffic, and the volume. And the tag could also include geolocation optionally. The victim then decides what to filter in case of DOS, and it sends the filter or allow message to the ISP that specifies the flow, the tag, the direction, and the duration of this filtering. And the ISP deploys this in its switches. The route query asks what's the best route to my prefixes. The ISP collects the routes from its border router, the best routes only to the given prefix, and it sends the list of the AS paths to the victim. Route demote asks the ISP to demote all routes to the given prefix that have certain AS path segment, because presumably this AS path segment contains the attacker. And the ISP demotes these routes and chooses the next best route that it knows about. I should mention at this point that the ISP has full control whether it will grant some request, it will serve some request or not. So if, for example, the customer asked for the route demote that would demote very well preferred route, the customer route, and force the ISP to take a peer or a provider route to go to the customer, the ISP could refuse to do that. So ultimately, it's up to the ISP to decide to have its own policy how it will handle requests and which requests will be granted or not. How we authenticate the ownership of the prefix, I said this is the major requirement so that someone couldn't misuse SENSS to ask for control of traffic or routes that do not belong to that network. There are multiple ways that the victim can prove that it has the authority to speak to a prefix. One way, if the victim is direct customer of the ISP could have a database that associates public keys of the machines that are allowed to speak for the prefix with the prefixes. So the victim would sign up the way it talks regularly with its ISP, it would sign up using some interface, some web application for this service. It would upload its keys, it would authenticate itself, and that would go into a database. Another way would be to use RPKI. The victim could present the ROA certificate that associates the prefix with the public key. The victim could also be under such a heavy attack that it cannot communicate to an ISP, especially if this is a remote ISP. In that case, the victim could offload this capability to a proxy in a different network. To offload the capability to speak to the prefix, the victim would just use its own public key to generate, private key to generate a certificate that, that gives the ownership of the prefix temporarily to a proxy. So I'll give you a few examples of how SENSS would help handle certain types of attacks in either isolated deployment, sparse deployment, or within an ISP. So in isolated deployment, there's a victim and its direct ISP deploying SENSS. The ISPA deploys a SENSS server, victim deploys a client. And imagine that victim is under direct flood. There are several cases that could happen. In one case, the victim would be able to identify the signature of the attack, but the attack is so heavy that it cannot be handled at the victim. In this case, the victim can send a control message to its ISP with the signature. This is the header level signature, not the payload signature. And the ISP would simply deploy filtering at the exit router to the victim. If the victim is under heavy attack, it cannot identify the signature. It could ask the ISP for the observation of traffic. When the observations come back, the victim could identify this link F2A as the link that now carries heavy traffic, and it would then send a control message saying that all traffic with tag F8 in destination being the victim's prefixes should be filtered. The victim could also periodically, when it's not under attack, issue traffic observation messages trying to learn what are the links that usually carry its legitimate traffic. This could help when the attack happens to reason about the potential collateral damage. So in this case, link AF is a good candidate for filtering because it had no traffic before the attack and now it has a lot of traffic. Notice that in all these cases, there is no requirement for the victim or the ISP to differentiate what is legitimate and what is attack. In the case of reflector attacks, the one potential defense that can be done using SENSS is that the victim can net all its outgoing traffic for the affected service. So the affected service in my example is DNS. The victim is under DNS reflection attack. What the victim would do is it would net all its outgoing traffic to port 53 using the gateway VN, and it would restrict the source port numbers to certain range. It's up to the victim to choose the size of this range, and it can change it anyway, anytime it wants. So in this case, the range is 1,000 to 2,000, and the victim then sends two control messages to its ISP. The first message says, asks the ISP to allow all traffic going to VN from port 53 to ports between 1,000 and 2,000, and the next message asks to drop all the other traffic going to the victim's prefixes from port 53. So this surgically removes all the reflector attack. In case that the ISP is only deploying both the SENSS server and client, and it has customers that are not technically savvy, they don't know anything about attacks, they just want to be able to say, I'm under attack, and the ISP will handle it for them. The victim in that case contacts the ISP. It could either run a SENSS client and contact it automatically, or it contacts through its usual means. The ISP would have to periodically analyze traffic again using SENSS to learn what is normal for each victim. When the victim is under attack, the ISP could run the detection module, which is it's an add-on module to SENSS, to identify what is the victim under attack and what type of attack, if there is possible header level signature or not. It could also, using SENSS, identify which links carry heavy traffic to the victim, and then again, using SENSS, it would implement the filtering. This is the example of how SENSS could handle attack in a case when it were deployed sparsely in the internet, but in multiple ISPs. So in this case, the shaded ISPs deploy SENSS. The victim V is under attack, and the victim would periodically, when it's not under attack, ask SENSS ISPs for the traffic observations. And from these observations, it can learn that most of its traffic usually comes on this upper link from D to A. When it's under attack, the victim again asks for traffic observations, and when it compares the observations before and after the attack, it is able to notice that this link L to S2 used to carry no traffic before, and now it carries heavy traffic. So this is good candidate for filtering because the projected collateral damage will be low. The victim then sends the filter message to L to implement the filter. I'll talk a little bit about the requirements for deploying SENSS at an ISP or a customer. So at ISP, SENSS can help provide added value to the customers. It helps diagnose the attacks with a separate module, detect and diagnose attacks, and it automates DDoS handling within ISP. It's a web application. SENSS server is a web application which can be run at any web server within the ISP. It has two-factor authentication for admin account. You can choose to use RPKI, or you can choose to use database and hand populate it to associate prefixes with the public keys that can speak for these prefixes. And you supply the IP addresses of your switches and the credentials that helps the SENSS automatically access the switches and enforce the rules. At the switch level, for traffic control and observation, SENSS needs either SDN, if your ISP is SDN enabled, or if it's not, we can observe using SNMP. We can control traffic using either flow spec or access control rules. For route observation and filtering, we talk directly to the router software. We've currently implemented support for Quagga, but we can go beyond that if you have something else that you're running. At the customer, the SENSS can help the customer engage ISP in the attack mitigation in an automated fashion, and it can help diagnose and detect attacks. At the SENSS client is a standalone Python program. Again, the admin account requires two-factor authentication, and the node that runs SENSS must have the proof of authority to speak for prefixes. So it either must have the ROA that binds its public key with the prefixes, or it has to be in the ISP's database as the node that is authorized to speak to a prefix. And in isolated deployment, you would supply the address of your ISP's SENSS server that you want to talk to. So I'll talk a little bit about the performance. We've evaluated SENSS in two ways. First, we've evaluated through simulation to see how this would work at internet level deployment. Could it really handle attacks if it were sparsely deployed? We've done very thorough evaluation at an internet level topology using different patterns of legitimate and attack traffic. We've also looked at the traffic variation in legitimate traffic. You've noticed that when I talked about certain attacks, I said, well, you observe traffic before the attack, and then you observe traffic during attack, and that's how you learn where to filter. That wouldn't work well if the legitimate traffic fluctuated a lot and went pretty much everywhere. But that's not the case in all legitimate traffic traces that we've analyzed. The traffic really stays in certain parts of the topology, and it doesn't fluctuate a lot. So even if you were to query twice a day, you would still have a good idea where your legitimate traffic usually goes, and your collateral damage from filtering would be low. We've found that in early adoption, the ISPs could help their customers mitigate 100% of direct floods and reflector attacks. And if SENSS were widely deployed, more widely deployed, so it's still sparse deployment, it's still on 1 to 2% of ISPs in the internet, but it's more than just a single ISP deploying this. In that case, there would be much wider range of attacks that we can handle. We could handle crossfire. We could handle attacks that are very widely distributed, spoofed, really hard to differentiate from legitimate traffic. We could handle attacks that are BGP prefix hijacking attacks, in which case you really need deployment farther from the victim to be able to correct fake routes. And the deployment at Tier 1 and Tier 2 would really help not just their direct customers, but everyone in the internet be protected. We've also implemented SENSS, and we've tested in emulation how fast it can work and what's the level of parallelism that it can support. So we've tested this on the TerLab testbed using topologies from Topology Zoo. These are real ISP topologies. The largest one has 186 switches. And so when we tested this, we've sent parallel requests to SENSS from multiple customers, which will rarely be the case that multiple customers are under attack at the same time, but we wanted to see what happens, what level of concurrency it can support. And so for 100 concurrent SENSS queries, it took under 5 seconds to handle them. This includes everything from RPKI authentication to gathering, putting the observation into the switches, gathering the responses, and sending back to the victim. For control messages, the traffic control is also under 5 seconds. The routing control takes longer. It takes about 25 seconds for 100 concurrent queries. And the reason for that is simply the telnet sessions between the SENSS and Quagga take time to set up. So we could optimize this in the future. So I'll conclude by saying that distributed attacks today are handled in a way that leaves something to be desired. There are definitely good solutions out there that can help with certain types of attacks, and they can work for certain types of networks. But what is missing today is this automated collaborative solution where you could, on demand, engage other networks to help you handle the attack. So we believe that we are complementary to the current solutions, and we are useful in a variety of settings. We'd really like to have people test drive this, talk to us. We're very motivated to have tech transition and willing to help put in new features and work with your network to make this right for you. So this is our project page where you can get more information. You can also get our source code. And if you want, we can set you up on the TerLab with an experiment to try this in a safe setting. So thanks. Reach out if you need more information. Thanks for coming.
Okay, we have time for just 1 or 2 questions. Do we have anybody that has a question? And if so, please raise your hand so we can get you a mic. So I guess we have no questions. I do have a question for you, and it's great to see what you've done in simulation and using some of the actual sample data and real data, but have you been able to explore using this either in Los Netos or in the Cenic venue with some sort of eating some of your own dog food, so to speak, that is deploying this in a test case scenario with live either Los Netos or Cenic?
We haven't had a chance yet, but we would really love to do that. So after this talk, I'm actually going to talk to Cenic Fox and see if there's a way for us to do that.
Yeah, I think that's, certainly Los Netos as a regional provider and your linkages at USC to Los Netos, there ought to be some opportunities there as on the commercial side of things, as a commercial ISP. Cenic may be more challenging in that regard because of what you've described, although there could be some tests there. So I think that there's some interesting opportunities there. So thank you very much.
Thanks.